Friends. Now we're looking at question 2 of 2025 AP Physics C Mechanics free response questions. So this one involves some springs. You've got two springs on either side attached to a block, and one has spring constant K, the other 2K. And so what I did, if you have this on paper, you can just write on it. What I like to do, and so I encourage you to use lots of scrap paper when you do this kind of thing. So I want to draw this for myself because I want to notice the details. I want to take notes on here so I can write K, 2K, all this stuff. And then right below it, I draw what's happening, right? So this is moved to X. I know, beautiful artwork here. Such convincing springs, but you know, you'll have to move past that admiration to do the physics. So when this is brought to X equals X1, so they want to know, basically they give you a bar chart and they want to see, can you quantify and compare the potential energies of the springs in the springs and the kinetic energy. So the potential energy in spring A, 1 half kx1 squared, and then potential energy in spring B. Spring B is 2k, is the constant, so it's 1 half 2k x1 squared, so that's just kx squared. And the kinetic energy is 0. It's released from rest at that point. When we draw the bar chart, that means that UB should be roughly twice as high as UA. You've got the grid lines on there on the response paper, so you should be able to get that. And then K should look like 0. Okay, so that's question part A of the question. Now it's released. Oh, and they want you to find an expression for the velocity when when the block is at position x equals 1 half of x1. Okay, and so what we do is we set up the conservation of energy equation. The potential energy plus the kinetic energy plus the work in the beginning. So, but there's no work here, so we leave that out. Equals the total energy at the end, UF and KF. I found the effective spring constant here rather than finding the two potential energies separately. I just found one potential energy. It's basically like having springs in parallel. And so the effective spring constant is 3K. It's just K plus 2K. We get 3K. So the total potential energy is 1 half 3KX1 squared. No kinetic energy in the beginning. At this point where it's halfway, so it's 1 half 3K, 1 half X1 squared plus 1 half MV squared. We don't know V. In fact, V is what we're looking for. We just leave the M in there. This is just solving a bit of work, algebra, nothing too complicated, but I wanted to kind of write out my steps as I was doing this. And I end up with this expression that 9 over 4 kx1 squared over m equals v squared. Take the square root and we simplify, bring out the square roots that I can take, and I get v equals 3x1 over 2 times the square root of k over m. Good. So one thing to check here would be interesting, right? So k, what are the units? Well, k, the units on k are actually interesting. They are kilograms per second squared, and then divided by m. So this is all in the square root, right? And then the m is kilograms, and we've got the x on the outside, so it's meters. This simplifies. You get kilograms canceling out the seconds on the bottom, square root, meters per second. That's velocity. That's what we want, just to kind of check what's going on with the units. Part C, so now we've got, this is on it's on a new surface. They give you the graph in scenario 1, where it's just oscillating back and forth on a frictionless surface. And then scenario 2, it's on a new surface where there is friction, but they tell you that the period's the same. So we want to take note of that. And again, if I'm doing this, I want to see these two graphs, one right above the other, so I can line them up. Right? I don't know exactly what it looked like on your answer key, or not your key, but your answer booklet where you're putting them. But I would want to, get this where everything is lined up, so I can just draw one graph right below the other. Now, the graph they give you is position. The graph they ask you to make is kinetic energy. The thing about kinetic energy is it's never negative. It's always positive. Because there's friction, the kinetic energy is going to be decreasing. And so the minimum kinetic energy is going to be when it's at maximum position. And when it's passing through the equilibrium, 0 position, that's where you have the maximum kinetic energy. So I drew dots, I've got my zeros where I'm at maximums and maximum min position, you could say. And I have maximum kinetic energy lined up with the 0 position here, right? I tried to. And then these are just getting smaller as they go down. Part D, relatively simple. They just say that, okay, now we've got a new block, larger mass. What's one thing that's going to change about the graph? Well, we have this equation, period is 2 pi root m over k. So if with no other analysis, just from this, we can say that the period is going to increase. And so that's going to be a horizontal dilation and stretching of the graph, right? So increase m, increase mass, increase period. It's a stretching of the graph. Thanks for watching. Don't forget to like and subscribe and share.